All right, so this is the last section of the sequence and series unit. We're going to do 1.5 and 1.6. Gotta put space. There we go. So the idea with this, what we're talking about is we're talking about this formula right here. Okay, it's when we're dealing with infinite series. So before I get to that, I just want to kind of show some basics. Here I have set up 4 different equations with different R values. My R values are listed here. Okay, let's just see what happens to our T1 when we have these different R values. It's not that complicated, right? We start with like a value of 1 and we multiply by 2 every time. That's our R, so these are our numbers. Or we start with like 1 and we multiply by half and it keeps getting smaller, -half or -2. None of this is new. I'm going to quickly graph it, what these look like, so you can kind of see the pattern of what's happening. So if we do this first one in red, right, we start it for term 1, we start with a value of 1, and then the next one's 2, so it's twice as high. Next one's 4, and the next one's 8. So obviously, as you can see, it's exponentially growing. Okay. The second one, on the other hand, blue, starts at 1, and the next one's half, so it's half as big, and then quarter, and then eighth. And so the idea is it's keep getting smaller and approaching 0, but never touches it. The third one, the pink one, it starts at 1 and then multiplies by -half. Oh, sorry, this should be a 2. There we go. So it starts at 1 and then becomes -1/2, and then positive 1/4, then -1/8. As you can see, it zigzags, and the zigs keep getting closer and closer to 0. And then the fourth one, down here in the purple, starts at 1 and then goes to -2, and then -4, and then -8. So again, exponential, just this time going downwards. Oh, sorry, hold on. Messed that up. This is +4. So it starts at 1, goes down to -2, goes up to +4, and then goes to -8. So it's zigzagging, but the zigs are going to keep getting bigger and bigger. So the 2 terms we need to know are convergent and divergent. Convergent means to come together, to converge on a single point. Divergent means to move apart, separate. So when we look at these lines, the divergent ones are the ones moving far and far away. So this red one, the exponential growth, which was this first one, is divergent because it's going away. The other one, this purple one, that's zigzagging further and further away, that's also divergent because it's getting farther and farther away from 0. Whereas when we look at these middle ones, the one, this blue line that was getting closer and closer to 0, or this zigzag pink one that keeps getting closer and closer to 0, those are both convergent because they are approaching something. So using that knowledge, we can actually use this formula, which will tell us what they are approaching. The idea with this formula, let me just cut it out so I can move it over. The idea with this formula, what you've worked with before was dealing with S at n. S at n means the sum of all the terms in a series when you're at the nth term. So for example, the sum of 14 terms, or the sum of 25 terms, or the sum of 1,000,000 terms. It doesn't matter, but there's always an n value. This formula, on the other hand, is saying a sum of all the terms in the pattern, which is impossible because it's the sum of infinity terms. It goes on forever. So what I'm trying to get you to see is that the divergent terms we talked about, this red line and this purple line, which basically means when R is bigger than 1, so like 2, 5, 20, whatever, or when R is less than -1, so like -2, -5, -20, any of those big value R's, that's when you get divergent. And it's not actually possible to find the sum of infinite because, as you can see, the terms are getting bigger. So if you keep adding to it, first you're going to add 2, then you're going to add 4, then you're going to add 8. It keeps getting bigger. It's never going to get towards anything. It's just going to get infinitely big. Whereas these 2 middle ones are cool. The numbers you're adding keep getting smaller and smaller until you're basically adding essentially 0. So those approach a real sum, and we can calculate it using that formula. So let's try one of them. Let's do this first one so we can figure out what it is. Okay, so I'm going to sub the numbers into the formula. So the sum of infinity, the sum of infinite terms in the series, is equal to term 1, which in our case we started with 1, 1 minus R, and then R for us was 1/2. So that's going to be 1 over a half. or 0.5, doesn't matter, whatever you want. Okay, 1 divided by a half is 2. So it's saying if you took all these terms, all the terms for infinity in this series, they would eventually add up to 2. That's like the cool magical thing. And it's just a simple number, it's just 2. This only works in convergent patterns. So the ones where they are getting closer to something. And that is when the R value is a fraction, but not any fraction, right? Like that, not that kind of fraction, that wouldn't work, like 1/2. Any fraction, positive or negative, that is less than 1 whole. Okay, so like 3/4, that's good. 4/3, not good. Any fraction like that for R is going to be good. So let's do one example. This one over here, 0.49, repeating. You want to write this as a fraction. A lot of times you're going to get this kind of question. You just need to break this into 2 parts is the first thing. So we got 0.4 is just 0.4 plus 0.09. And then the next number in the term is 0.009. And you can see the pattern is that every time you're dividing by 10, which also means we're multiplying by 1/10. Okay, so now we have enough information to do our formula. So the formula is sum of infinity, because we're going to basically add all these repeating 9s. We want to add them together to find out what they are. Is equal to 1 over 1 minus 1 over, term 1 minus 1 over R. So my term 1 was this one right here, the 0.9. So I got 0.09. Let me double check. Yep. Or you know what? Let's write it as a fraction just to make our lives easier. So this is 9 over 100, right? Because that's 2 decimal places, 2 decimal places. 1 minus, and then what's our ratio is 1/10. So 1 over 10. Okay. Then we're going to actually like do the math and deal with it. So 9 over 100 over 1 minus 1/10 is the same as 9/10. And then we have a fraction divided by a fraction, so that's the same as invert and multiply. So 9 over 100 times 10 over 9, okay? These will cancel out, so you get 9 over 90. We can divide them both by 9, 1 over 10. Cool. So now the original question asked, can we write this number as a fraction? And we said it's this, 0.4, plus this repeating nonsense. What we just did was we determined that the sum of all these repeatings, that's what S means, right? The sum of all these repeating terms is actually 1/10, which is the same as 0.1. So what we're really saying is it's 0.4 that plus 0.1. Because that's what all of those added together are, which is really just 0.5. Okay, which is really cool because it started out as 0.49 repeating is actually the same as 0.5. So those are the types of questions you'll deal with. If it's a decimal fraction, whatever, like we did over here, you just have to break it into the 2 pieces, the not repeating part and the repeating decimal part, and then use your formula, this formula. The reason we did the graph thing was just so that you could see. The other thing we didn't do was when like actually graphing the sum of these, but it's not that bad. You make a table of values, you plot the values. It just works like that. You just need to remember that this term only works when it's convergent, which means that you have an R value of these ones right here. Okay, that's it.